So welcome back. We're going to pick up right where we left off, talking about the heat treatment of steels and move on from the time temperature transformation, or the TTT or isothermal transformation diagrams that we discussed in the last lecture, and move into continuous cooling transformations. In this case, it's probably, if we really think about it, it goes into what might be a little more of a realistic view of heat treatment in some ways, but more of heat treatment that we would see in welding and other types of processes that we will run into that are widely used for processing metals. So as we move forward, we're going to have Lord Kelvin. As you probably imagine, Lord Kelvin was famous for a number of things, but he also was very practical in his approach to science. And so he really liked to sort of say that the practical application of science is really what lies behind why we look at things. So he wasn't really caught up in really sort of the fundamental or the pure science aspects of it. But it's surprising that the same man that made this statement would also have said that heavier than air machines will never fly at about that same time frame. So Lord Kelvin's famous for sort of both, one good and one bad. So we're going to get into a little bit more of converting these isothermal transformations to what we consider continuous cooling transformations, where rather than a fixed temperature we may apply, we're going to apply a fixed cooling rate to understanding really the decomposition of austenite into various different microconstituents. We're going to get in a little more of the mechanical behavior that comes out of this from these types of transformations. Sort of what do we expect when we have a bainitic or pearlitic or a martensitic type structure, and what type of mechanical behavior would come from that. And we're going to touch upon a very important application of a post-process or a follow-on heat treatment to a martensitic structure, where we actually start to consider tempering the martensite. And what that does is, rather than making the martensite, which in and of itself mechanically is viewed as rather hard and brittle, becomes a little tougher and gives it that sort of ductility and that ability to withstand crack initiation and growth. So we see from the 9th edition, once again, a number of pages to read here, and a few more practice problems. 3 of them are assigned. They're part of your homeworks that you need to turn in at the end of the lesson. But as always, I recommend that you do all of them, and we'll post the solution on Canvas at the end of the lesson, or after the lesson closes. So what we see is we have these important terminology as we move forward. A lot of them are the same. A couple other ones that we're going to run into. And the critical cooling rates are really specific to these continuous cooling transformation diagrams that we're going to talk about. Really what we're going to see is that the TTT and the CCT diagrams are really, at the end of the day, very similar. They really just need to be read in different ways of dealing with whether it's a isothermal heat treatment or a specific cooling rate. So what are continuous cooling diagrams? So if we really think of most heat treatments, we're not going to instantaneously cool from one temperature to another and hold at that temperature. Isothermal transformations, as we said, those TTT diagrams are only valid for constant temperatures. And if the temperature is constantly changing, that transformation, or the locations of those curves on that plot, are going to move around as well, depending on what that cooling rate is and how the cooling is performed. In continuous cooling, what we tend to see is, because we're not holding it at a single temperature, the time required for the transformation to actually begin and end, we consider it delayed. It takes longer because we're not holding it at that temperature. The kinetics tend to be slowed down because we're not holding it at these specific temperatures for very long, for the same lengths of periods of time. And so we ended up modifying. So a quick and easy way to think about continuous cooling transformation diagrams is they are just modified TTT or isothermal transformation diagrams. And typically the way they're modified is that the lines that we have get shifted to the right, or to longer times. And so the dotted lines in this, for this eutectoid composition, represent where they exist for a TTT diagram. But as we go to a CCT diagram, we just see that they're shifted to the right The bainite doesn't change a whole lot because we already have a pretty significant amount of undercooling. Martensite start, remember, is rather athermal, so whether it's continuous cooling or not, these are not going to move that much between a CCT and a TTT diagram. But it's this perlite where we really have a lot of longer order diffusion that we would need. We tend to see that we need more undercooling and longer times for these transformations to begin. Now, how do we read a continuous cooling transformation? We sort of hit upon that we still have the same shapes of C curves. These types of curves, the starts and the finishes, don't really change very much. The one thing that will go away in a lot of cases, as you start to see with these, is that you don't always see that 50% mark there. You have one or the other because you're going through these so quickly. It's a little more difficult to try to pick up. But let's think about, how do we read these? And so the way we read a CCT diagram is we need to actually, rather than just looking at the curves themselves, we need to add in the curves that represent the temperature or thermal histories that we're interested in, or these cooling rates. And so if we have a slow cooling rate, we see that it tends to take on a shape where we're at a temperature for a longer time. The slopes are a lot lower than what we have with a faster cooling rate. And in this case, what we see is the difference between forming a coarse perlite with slow cooling, or with a more rapid cooling, a finer perlite. And so what we tend to see is between these areas, we have these transformations occurring. We don't have a 50% line here because it's going to be a little tougher to pick up the actual amounts. But with these composition and these different cooling rates, what we tend to see is these different types of ways of looking at it. So with the continuous cooling transformation, we have to add in these types of curves, and we look from slow cooling to rapid cooling, in this case going from a coarse perlite to a fine perlite. And so in this one, we've taken away the bainite. It doesn't typically form in this case, but the austenite perlite will terminate just below that nose, so to say, in this continuous cooling transformation. And this is a eutectoid steel. So this is another difference that we have. But in this case, when we start looking at continuous cooling, what we're really starting to try to think about is, how quickly can I cool or run this material through a cooling cycle in order to start forming martensite, or 100% martensite. That's our big differentiator here between continuous cooling and time temperature transformations. And so this brings us into a concept of critical cooling rate. So if we were to take and look at the nose of this eutectoid CCT diagram where we have austenite to perlite, and if we go at cooling rates faster than about 140 degrees C per second, we are to the left of the nose of this curve, what we call this point where it comes around. And if we're to the left of that nose of that curve, we are at a higher cooling rate than what we would need to form any perlite at all. So at any cooling rate greater than 140 degrees C per second, we have 100% martensite. Now, we can also think in terms of a critical cooling rate of where we would start to not have a purely perlitic structure. And so that's another important consideration, because there's significantly different material properties between a 100% perlite and 100% martensite structure in this eutectoid steel. And so if we're at cooling rates below 35 degrees C per second in this case, and these rates are just specific to this alloy, we tend to have a purely perlitic. So say if it was 20 degrees C per second, we would have a 100% perlite structure. If it was 150 degrees C per second, we would have a 100% martensite structure. If it was somewhere in between, at say 75 degrees C per second, what we would have is a mix of martensite and perlite, and we would try to adapt that to determine how much martensite and perlite we would end up with. So slower cooling rates, perlite, faster cooling rates, and to go above this critical cooling rate here, we have 100% martensite.